I'm going to talk about an example of how we can use this technology to protect a brownfield system, and the brownfield system is going to be the factory that we have in the back. Before I go and talk about the factory specifically, I'm going to talk a little bit about how we kind of think about these assured reserve modes, and give a little bit of a little example of a prototype that we've built of the assured reserve mode architecture. Then I'm going to talk about how to implement that. What are some of the technical challenges to implement that? How does that fit with what SEL4 gives us? And then how do we build on what SEL4 gives us in the Kry10 OS to build this reserve mode prototype? And then I'll give a demo of how we use that in the factory. So the first thing I want to do is take what Lance has talked about with the reserve modes and this little matrix, and extend that a bit with this concept of system configurations. And so a system configuration is basically a specification of all the running components and connections on a system. So think of like a CamKit spec or a MicroKit spec or something like that. It's basically just saying these are all the things running on the system. It includes the operation components and the protection components of both of those roles. And often, kind of colloquially, we talk about these system configurations as each system configuration is a reserve mode. And then when we think about a system that takes advantage or uses ARMA, we think of the system lifecycle as a succession of these system configurations. So the system kind of starts up in one configuration, and at some point it changes to another configuration, and then to another one, and so on. And so as it goes, it switches between them, and then an ARMA system is kind of the collection of all the system configurations that make up that particular device or system. And last year, I kind of introduced a bunch of terms for different kind of dynamic systems, and this is an example of a semi-dynamic system where you're going from kind of one static architecture to a different static architecture to a different static architecture. And so the system changes, but it changes in a very known way. So as an example, we have 3 system configurations, and the one that's not kind of faded out is the active one. And so this is a configuration that consists of a bunch of operation components that are connected to each other. And the other ones are kind of in reserve, right? They exist, but they're not active. And so they define what the system looks like. And so we can see kind of the next system on this transition list has some of the same components, some of the same operation components, but it's got a different component there that's a dormant component because it doesn't actually exist in the system. It's a protection component. So if we switch, suddenly all of those components become active. Other ones that aren't in the system anymore become dormant. And we can keep going through that system, adding and removing components and switching between different configurations and go back. So that's just this idea of a system consists of kind of a sequence of different system configurations. So I want to do kind of show you what this looks like in practice. And this is based on a prototype of this ARMA architecture or ARMA technology that we've developed. Sits on top of the Kry10 OS, which is on top of SEL4, and makes use of a whole bunch of kind of features and properties that Kry10 OS provides for us, and then some applications that sit on top of that. And later in the talk, I'll go into more detail about what's in that yellow ARMA box. So, all right, this is a brief demo. What this is going to show is a simple system that consists of 4 configurations. So there's a base configuration, and then a configuration that has a C application running, another configuration that removes the C application and starts an Elixir application running, and then another configuration that changes that Elixir application and adds another application, Elixir application that'll communicate with each other, and then that can go all back to the start. So this is running on Kry10 OS. One of the things that Kry10 OS provides us, that's for the original time. Yeah, okay, cool. One of the things that Kry10 OS provides us is this really neat dashboard that shows us the running system. So I'll refer to that to show you what's actually running on the system. And the other thing is that I've implemented this prototype in Elixir, and so what that allows us to do is to do a remote connection into the server that's controlling the reserve modes and be able to directly invoke these switch commands through kind of like a command line interface. So let's see if this will work. So this is the video. So I start off, On the left, we see kind of what's running, and we don't really see any of the extra applications. So I'll invoke a switch. Excuse my slow typing. We'll switch to system 1, which will add a C component. When we do that, we see kind of stuff getting loaded here. And then when I reload this page, we see this C component has been added. This is the only thing that changes, by the way. None of the other components are actually restarted or stopped. The system isn't restarted. So we then switch to the next system, which adds an Elixir component and removes that C component. And then we switch again to the other system, which is going to add another Elixir component here when we reload. So it shifts over a bit. There's these 2 Elixir components, and they're connected now, and they have this kind of little echo server protocol. And then we can keep going, looping through that. The other thing we can define is what are allowed transitions and what are not allowed transitions. And so there's a couple of attempts to transition against the rules that didn't work, and then we can switch back to the base, which is allowed, and we see all the extra components are gone again. So that's kind of a very basic example of how that works at runtime. So what I want to do is kind of dive into that. What do you need to actually implement something like this? And then how do we do that? What are some of the technologies that we have developed or use that we've developed in Kry10 OS to do that? And then go into the demo. So some of the main technical requirements for doing this is you need to have some concept of system configurations, right? So some way to define your whole system, to specify that, and then instantiate one of these components. And you need to be able to reason about the configuration. So if you have 2 configurations, you need to find out what's the difference between them, what's the delta, what's actually changed. We need to have support for dynamics, right? This is a semi-dynamic system, like I said, so we want to change between pre-configured system. So we want to be able to add and remove components and do the resource allocation and deallocation that requires, right? When we're adding an application, we need to allocate a whole bunch of resources for it. When we remove it, we need to take those resources away. And we need to be able to do that with connections between components as well, right? When we add components that are connected, we need to create those connections. But when we change components or update them or remove them, we need to be able to remove the connections. We need isolation, so we need to have protection between the components, the operation and protection components. You can imagine if you've got one of these monitor components and an operation component that gets compromised, you don't want that to be able to stop the monitor component, for example. Or if you've got a guard component or a hunt component or something like that, that needs to be protected, right? So we need this isolation. We need protected access to various resources. So if we've got these dormant components on the system, we don't want someone to be able to compromise those as well. And then finally, assured is in the name. We need assurance. We need assurance that the operations actually occur correctly and that we have these properties. So if we take these kind of requirements and we look at SCL4 and how it kind of meets these requirements, system configurations, SCL4 kind of the base gives us capdl, but we also have just raw SCL4 calls to create system configurations. We have things like camkits, microkit specifications, and so on as well. In terms of dynamics, SCL4 gives us a lot. We've got untyped retypes. We've got capabilities. We can transfer capabilities. We can revoke capabilities, and so on. These are all really powerful mechanisms for building these kind of dynamic systems. So we're pretty good there. One of the draw cards of SCL4 is the isolation through capabilities, C spaces, V spaces, and so on. So we're really good there. And then assurance, we have a verified kernel that gives us assurance about all these, this dynamic properties and the isolation and so on. So we're really good there as well. But SCL4 doesn't give us reserve modes for free, right? We still have to do a lot of work for that. So if we look at things like capdl, it's at the same time a bit too specific for doing something like reserve modes, but also not specific enough in terms of when you do a capdl specification, you have to specify exactly what an application looks like inside, a component looks like inside. What's its C space look like? What's its V space look like? What caps does it have, and so on. But it's also not specific enough. You don't have control over where those resources actually come from, right? You don't specify kind of what untypes back all those resources. The loader kind of figures that out for you. So we need kind of, at the same time, less specificity, but also more specificity. In terms of dynamics, we have kind of the mechanisms, but not the policies of how to use them to create a system that's dynamic enough, but that allows you to kind of add and remove these components without drowning in bookkeeping. You can imagine like having to track all the capabilities and stuff gives you a big bookkeeping requirement, and you don't want to kind of drown in that. But we also want flexibility for components to do internally whatever they want to do. We don't want to we don't want to enforce policy into what components look like and how they structure themselves internally and so on. And we don't want to start fiddling with the internals of components as well. So we want to have kind of minimal policy but still enforce the isolation. And then with regards to connections, it's also not obvious how to set SCL4 up or set up SCL4 communication primitives such that you have this flexible kind of connection, ability to flexibly connect and disconnect components as you add and remove them. So a lot of times we'll have you know, a kernel object like an endpoint that's shared between two components, and they have caps to that. And if you want to remove one of those applications, you might end up removing that endpoint, and then someone no longer has a cap to that endpoint, but they don't know that that endpoint's gone, and that can cause problems. Or you might have to kind of dig into the internals to, you know, to kind of change data structures so that they know that the cap's gone or the new cap replaces it or something like that. It can get really complicated, and so there's no kind of guidance on how to do that properly. So this is kind of where where Kry10 OS comes in our implementation of ARMA on top of that. As an overview, this is kind of what the architecture looks like. We have SCL4 on top of that. We've got some Kry10 OS services, in particular the root task and the message server are important for ARMA. And then we have kind of the ARMA layer on top of that. And the main thing there is this reserve mode server, the RM server, and that basically has two things. That's responsible for switching the systems. So it has two things inside it. It has all of the system configurations that make up the ARMA system. So, you know, this kind of configurations that we transition between them. And then the logic for actually using them, the logic for comparing them, figuring out the deltas, deciding what the actual steps are to change from one system to the other, what needs to be added, what needs to be removed, and so on. And then the actual data that needs to be kind of, you know, the binaries and so on that have changed that you need to be able to load and so on. The actual kind of loading and unloading of applications and components is done in the root task. So that's a highly privileged component that kind of knows how to set up the resources for that and take them down and so on. And then in the ARMA layer, again, we have this RM manager. So if you think of the RM server as the mechanism, the RM manager provides the policy. It decides when to perform switches. So based on things that happen in the applications and signals that are sent to the manager, it can decide when it's time to switch a system. So that's kind of the general thing. I'm going to highlight two mechanisms that we have in Kry10 OS that enable us to do these reserve modes. So the first thing revolves around resource management and how we set up components or applications such that we can perform kind of dynamically add and remove applications, stop and start them, and so on. So the challenge here is components have a lot of resources, right? We have the virtual address space, we've got all the pages, we've got thread control blocks, we've got our stacks, we've got our communication endpoints, device I/O accesses, C nodes that keep track of all our capabilities and stuff. There's a lot of stuff there, and it's potentially quite complex bookkeeping, keeping track of all of that. So what we do in Kry10 OS is we basically build a sandbox for an application, for a component, based on an untyped. So we take an untyped, we reserve an untyped for the application, and then we allocate everything for that application from that single untyped, right? So all of the endpoints that it needs, the C space that it needs, the page mappings, the virtual address spaces and stuff. Thank you. So we allocate all of that from that. Then we load the code in and run it and so on. And then if we need to reset the sandbox for whatever reason, for example, it crashes and we need to restart it, we need to stop it, remove it from the system, then rather than having to manually keep track of all these things we've allocated, we can just revoke that untyped memory. And all of those things disappear. Right? So we really kind of delegate that bookkeeping to SEL4. SEL4 is already keeping track of all this stuff. And so if we allocate it all from the single untype, it all disappears, which means we don't have to do that bookkeeping. But the cool thing is all that revocation is also verified. Right? So we know that SEL4 is going to do that correctly. And so that's kind of the only garbage collector we need. We don't need to implement our own bookkeeping, our own garbage collector. We don't need to verify our own bookkeeping and our own garbage collector. We just rely on SEL4 to do the right thing. So that's been super helpful, this kind of model for doing all of this dynamic stuff. So here's kind of an example of how that goes. We start off, we want to start an application. So we have some kind of outer bookkeeping that we need to do for it. But otherwise, when we want to start an application, we allocate this big untyped, and then we allocate everything inside that big untyped. It runs. We typically, give it some memory. We give it C nodes where it can track things. It's got its main thread. We also give it a whole bunch of working untyped as well. So the application itself, or the component, can decide what else it wants to allocate, how it wants to allocate. It can share memory with other servers and other components to give them resources to use on its behalf and so on. So it can, we don't control what it does with the rest of its memory, with the rest of its resources. We kind of share them and so on. But then when we're done, when we want to revoke all that, we just take the untapped away and it's all gone, including what's been shared and given out to others and so on. So the other challenge is connection. So I've talked a little bit about that. Connecting and disconnecting is typically hard, right? We kind of ran into this problem when doing things like CamKIS and so on, which is one of the reasons why we didn't really explore further with dynamics in CamKIS, was because dealing with these connections is hard. If you directly give someone kind of a cap to your endpoint, then you have to manage those on both sides. If you remove one of the sides, it ends up a management problem. You can start kind of, figuring out what to rewrite in the other applications so that they know that things have happened. But it's complicated. And it's complicated to do that in a flexible way without forcing some kind of structure and forcing some collaboration on the communicating components. So what we do in the Kry10 OS is we have a message server that mediates the creation of connections between components. And so one of the things it does is it uses untypes that are donated from the components that want a connection. And so basically it doesn't use its own memory for doing these connections, but it uses memory that's donated from the things that want to communicate, which is really great in a dynamic system because you don't have to worry about running out of resources when you're managing these things, because people give you resources when they want you to manage them, which is good. The other thing is we have these kind of two sides of a connection when a client and a server communicate. If the client goes away, it removes its part of the connection, but the server can still communicate or still has that part of the connection, and it can find out that the client has disconnected in a nice, clean way. When the client connects again, then the message server can facilitate this connection again, and they can communicate again. So this is really nice for when you're connecting and disconnecting all the time. All right, so last little bit, the demo-y part. So this is going to show kind of how we apply this to the demo we have in the back. And the demo in the back isn't actually showing this, right? So this is a little bit different. The general scenario is we have this factory. The general architecture of the factory is we have the machines, so all the red bits, the things that move, and they're controlled by a PLC, a programmable logic controller that runs the code that kind of controls these things. And the PLC communicates with a Raspberry Pi that's on there as well. That's part of the factory, and that acts as a dashboard. So the Raspberry Pi gives you a web-based dashboard that you can control things. It also connects to the, well, indirectly connects to the internet and to the cloud, and you get a cloud dashboard as well. And then in our scenario, we have an attacker that connects either to the Raspberry Pi and compromises that, that's running Linux, or just directly connects to the same network and is wanting to send malicious commands or malicious requests to the PLC. And the PLC speaks industrial control system protocol called OPC UA, and so it can send messages to that. One of the things is that this factory is not very secure. It's a nice demonstration of what a real industrial control system looks like, because they're also not built to be secure typically. So The OT is connected, so OT is operational technology, is what runs the factory, is connected to kind of the information technology and internet pretty much directly, right? So you can get in here and do things on here without any authentication. It's running commodity OSs like Linux on the controllers, which can be compromised. And the communication going between the node and the PLC is unencrypted. We've got OPC UA that's unencrypted, MQTT that's unencrypted, and so on. Now, all of those problems can be solved, right, if you rebuild the thing and use the right technology. OPC UA supports authentication and encryption and so on. It's just not being used. You know, there are potentially more hardened things than the Raspberry Pi operating system. You don't have to connect the OT to the IT. We know how to solve these problems, but it's an existing system and we don't have control, right? This is a brownfield system. We can't reorganize the system, re-implement and so on. We've got this, but we want to protect it. So what we introduce is kind of this guard component, and the guard component sits between the external communication, the PLC, and it proxies and filters that communication. And so its job is to filter out any potential attacks, detect any potential attacks, and protect this existing system from the attackers. The general architecture of the software running on the guard, it's running on Kry10 OS and the ARMA, and it basically has two Ethernet connections, one for the inside for the PLC, one for the outside talking to the Raspberry Pi or the attacker, and it's got this filter inside. So any communication coming from the outside has to go through the filter and then go out. It also has some extra components, a UI component that tells the state of the system, whether it's being attacked or not, and then a log component that can log traffic for further analysis later on. The reserve modes, so the configurations of the factory, there's 4 of them. There's normal with no protection, where there's just kind of a proxy component where all the traffic goes through. There's a filter mode where it filters out known attacks and stops known attacks. There's a filtering plus logging mode where it filters out attacks, but it also logs everything for further analysis. And then there's a disconnected mode. If you're really desperate and in trouble, you just remove that proxy in the middle, and there's no more connection between the 2 Ethernets, and no traffic can come through. All right, here's the last bit, demo. So this is kind of showing the same things that we show on the factory, but with these reserve modes automating things. So we can run an attack on the factory. This is one of the attacks that I think drops something on someone. So we run that. It kind of goes, it has a piece, but instead of loading the piece into the high bay warehouse, it drops it on the guy standing there taking pictures. You don't want that to happen in your factory. So we don't like that, so what we're going to do is we're going to turn on the filter connection, so the second mode. So this is the UI. This UI is running on the gateway device as well. So it's turned into the filter mode. We can look at the dashboard to see what it looks like, the architecture. And then we see that we've got this OPC UA filter in there, right? So traffic is going through there and then through the other network. We can now run the attack again. I'm showing you that it's changed. So we've reloaded and updated the OPC UA filter because we've added filter rules now, not just proxying. We'll run the attack again, and we'll show that the attack gets blocked when we do that, eventually. So it's just going to get a whole bunch of Python errors. But it also gave us a little flash saying, hey, it's been rejected. So I repeat the attack a bunch of times, and what I have in there is that if I've done the attack 4 times, it's going to automatically switch into a different mode, into a logging mode. So there you go. I've done the attack a bunch of times, and it's switched into a logging mode. So now what it's doing is it's filtering, but now it's also logging all the traffic, all the OPC UA that's going on there, and we've added the logging component as well. So we run that for a while. And it's still going to filter out the attack. But sometimes, attackers are clever, right? What Boyd said, things change all the time. And so they come up with different attacks. Once they see that these attacks are filtered out, they might come up with different attacks that we don't know about. So this is another attack that we can do, and we call it the dance or the haywire attack, where we take control of the factory and we just make it move, like do random things, right? Rather than doing the work it's supposed to do, we just make it do crazy things. We didn't know about this attack, and so it gets through. We freak out a little bit, and we don't know what to do. We've got all this log coming in, but it's too much to process right away. We're going to need to have some time. So we switch to a disconnected mode. In this case, we remove that proxy. There's no more communication going in or out of the factory. It's disconnected from the network. We have time to kind of think about what's going on, come up with new solutions, new mitigations, and then update the gateway with the new mitigations and change to that new mode. So I think that's it. We can switch back once we're ready. We can switch back to the normal mode. So that was the demo part, and I think we've run out of time for your conclusions.
Let's just go to the conclusion side. We can take questions now.
I think, okay, if I can, I can't do this. Can't even find the arrow. Go ahead, start
All right.
questions.
Thank you.
So what's the point of running without filtering and logging in the first place? That seems rather negligent.
I mean, you can do that, but the whole point is logging. You don't necessarily want to do all it. You don't necessarily want to do so much logging all the time, right? Normally they run with nothing. You can run with filtering, but you might. This is a demo, right? It's an example, but you might not. You might need to update your filter rules, for example, to be more strict. Right? You may have kind of gentle filtering. You might update them to be more strict, for example.
A more technical question. What's the difference between your, what do you call it, limited dynamic or whatever?
Semi-dynamic.
Semi-dynamic, compared to a static architecture where some of the connections are discretionary?
I think if you have a static architecture where some of the connections are discretionary, then you're kind of more limited in what you can do. You have to choose in advance what you're going to do, whereas this gives you a lot more flexibility to add in new modes, for example, on the fly and change to them. Also, changing kind of implementations of components and stuff gives you more flexibility.
Okay. We have time for one more question.
Right. With the existing nodes continuing to operate like in a non-stop system, and the changes were dynamic only to the additional nodes and their connections?
Yeah.
Great.
Yeah.
Okay.
Yeah. Yeah. So everything that didn't change between configurations kept running, and you could see that kind of in the dashboard. You could see still stuff going on in the console and so on.
I think it's important to note that we do have more sophisticated configurations. It's just we try to get something we could talk about here in a short period of time.